In North African and Eastern European theaters during the Second World War, two military vehicles encountered identical operational conditions: extreme terrain, supply chain fragility, maintenance constraints, and operational tempo demands. One vehicle was engineered for versatility and structural robustness. The other was designed under severe material scarcity and prioritized weight reduction, mechanical simplicity, and field maintainability. Under doctrine, the first should have dominated. Under physics and logistics, the second consistently performed better. The Volkswagen Kübelwagen was not superior because it was better engineered in absolute terms. It was superior because its design constraints aligned with operational reality in ways the Jeep's design assumptions did not. Where the Jeep required replacement parts, specialized tools, and logistical depth, the Kübelwagen required improvisation, minimal tooling, and local adaptation. Where the Jeep's weight compromised mobility in sand and mud, the Kübelwagen's lightness became a performance multiplier. Where the Jeep's four-wheel drive system added complexity and failure points, the Kübelwagen's rear-wheel drive simplicity reduced maintenance burden. This is not a story of American engineering failure. It is an analysis of how design premises embedded deeply in procurement philosophy, industrial capability assumptions, and operational doctrine created performance outcomes that contradicted institutional expectations. The Jeep was not defeated by a superior vehicle. It was defeated by the operational conditions its design did not prioritize. How can a vehicle designed under resource scarcity structurally outperform one designed under resource abundance? The answer begins with understanding what each design premise optimized for, and why those optimization choices created fundamentally different vehicles despite superficially similar missions. The American Jeep emerged from a 1940 procurement specification calling for a light reconnaissance vehicle with four-wheel drive, quarter-ton payload capacity, and maximum versatility across roles. The specification reflected institutional confidence. American industrial capacity could produce a vehicle capable of performing multiple mission types: reconnaissance, cargo transport, weapons mounting, casualty evacuation, command and control within a single platform. This versatility was considered a strength. The vehicle would be robust enough to survive rough handling, powerful enough to traverse obstacles, and adaptable enough to serve any tactical requirement. The design philosophy embedded several assumptions. First, that four-wheel drive would guarantee superior mobility across all terrain types. Second, that structural durability through mass and material quality would ensure operational longevity. Third, that a versatile multi-role platform would provide better force economy than specialized vehicles. Fourth, that American logistical infrastructure could support the maintenance and supply requirements of a mechanically sophisticated vehicle. These assumptions shaped every specification decision. The Jeep's final design weighed approximately 1,100 kilograms in combat-loaded configuration. Its four-wheel drive system utilized transfer cases, locking hubs, and differentiated gear ratios to provide power to all wheels simultaneously. Its liquid-cooled engine required radiator fluid, coolant pumps, and temperature management systems. Its suspension used rigid axles with leaf springs, optimized for load-bearing and obstacle negotiation, rather than weight minimization. The vehicle could mount machine guns, carry stretchers, tow artillery pieces, and transport supplies. It was, by institutional standards, exceptionally capable. The German Kübelwagen emerged from different constraints entirely. By 1938, when development began, Germany faced material shortages and anticipated wartime resource scarcity. The specification called for a vehicle that could be manufactured with minimal strategic materials, no rubber in short supply, no complex alloys, no systems requiring scarce components. The design had to be maintainable with basic tools by soldiers with minimal mechanical training. Weight had to be minimized to reduce strain on underpowered engines built from available materials. Mechanical complexity had to be eliminated wherever possible. Ferdinand Porsche's design team approached the problem by identifying what could be removed rather than what could be added. Four-wheel drive was eliminated. It required transfer cases, additional drive shafts, and double the number of powered wheel assemblies, all adding weight and complexity. Liquid cooling was eliminated, air cooling removed radiators, water pumps, hoses, and the logistics of coolant supply, while improving cold weather reliability. Structural mass was minimized through careful material distribution. The body was thin stamped steel with minimal reinforcement, relying on geometric rigidity rather than material thickness. The resulting vehicle weighed approximately 700 kilograms in combat configuration, 400 kilograms lighter than the Jeep. This weight difference was not incidental. It was the primary design objective because weight directly determined ground pressure, and ground pressure determined mobility in yielding terrain. Ground pressure is calculated as vehicle weight divided by the contact area of tires with the ground. The Jeep's 1,100 kilograms distributed across 4 relatively narrow tires created ground pressure exceeding 1.5 kilograms per square centimeter under typical load. The Kübelwagen's 700 kilograms distributed across 4 wider lower pressure tires created ground pressure below 0.9 kilograms per square centimeter. This difference fundamentally altered how each vehicle interacted with sand, mud, and snow. In firm terrain, hard-packed roads, rocky surfaces, frozen ground, higher ground pressure provides advantages. Tires bite into surface irregularities, four-wheel drive maximizes traction, and vehicle mass aids stability. American doctrine assumed these conditions would dominate. Procurement specifications emphasized obstacle negotiation, the ability to climb steep grades, ford streams, traverse fallen logs. The Jeep excelled in these scenarios. But North African and Eastern European combat zones were not characterized by firm terrain. The Western Desert campaigns occurred primarily in sand, fine-grained, yielding material where wheels sank proportionally to ground pressure. The Eastern Front featured deep mud during spring and autumn Rasputitsa, when freeze-thaw cycles turned roads into liquid morass. Winter operations occurred in deep snow, another yielding medium where flotation mattered more than traction. In yielding terrain, the physics reverse. Lower ground pressure allows a vehicle to remain on the surface rather than sinking. Wider tires distribute load across more material. Lighter weight reduces the total force. The compounding effect of these design differences created a vehicle that was objectively inferior on paper, but operationally superior in practice. The Jeep had higher horsepower, four-wheel drive, greater payload capacity, and better obstacle climbing ability. The Kübelwagen had lower weight, simpler mechanics, better fuel efficiency, and superior mobility in yielding terrain. American procurement doctrine valued the first set of characteristics. North African and Eastern Front operational reality rewarded the second set. The institutional failure was epistemic. American engineers and procurement officials were not incompetent. They designed exactly what doctrine specified. The doctrine was wrong because it assumed conditions that did not match operational reality. It assumed firm terrain, reliable logistics, trained mechanics, and multi-role employment would define success. Operational reality featured yielding terrain, disrupted logistics, undertrained mechanics, and single-role tactical employment. The Kübelwagen was designed for the conditions that existed. The Jeep was designed for the conditions that were assumed. This divergence was invisible during peacetime testing. Test ranges featured obstacles, grades, and firm surfaces. The Jeep excelled in these conditions. No institutional testing program replicated hundreds of kilometers of deep sand under combat tempo with minimal maintenance support. The conditions that revealed the Kübelwagen's advantages only emerged during actual combat operations when it was too late to redesign vehicles or retool production. The design premises embedded at the start: versatility versus specialization, complexity versus simplicity, capability maximization versus constraint optimization determined all subsequent outcomes. These premises were not neutral technical choices. They reflected institutional values, industrial confidence, and doctrinal assumptions about what warfare would require. When those assumptions proved incorrect, the vehicles designed around them could not adapt. The Kübelwagen's design premise aligned with operational reality. The Jeeps did not. That alignment, established before either vehicle entered production, predetermined which would dominate under actual combat conditions. Design premises established what engineers optimized for, but vehicles operate within logistical and organizational systems. a vehicle's theoretical capabilities matter less than its practical availability under field conditions. The Kübelwagen and Jeep diverged not only in design philosophy, but in the maintenance infrastructure, training requirements, and supply chain assumptions embedded in their operational employment. These latent conditions invisible during peacetime evaluation, decisive during sustained combat determined which vehicle could maintain operational availability when logistics failed, when mechanics were undertrained, or when units operated beyond supporting infrastructure. The American military logistics doctrine assumed forward supply depots, trained maintenance personnel at company and battalion levels, and regular resupply cycles. This assumption was reasonable given American industrial capacity and logistical experience. The Jeep's maintenance requirements were designed around this infrastructure. Routine service intervals specified in technical manuals assumed parts availability, proper tools, and time to perform procedures correctly. Major repairs assumed transport to battalion maintenance companies with trained mechanics, proper lifts, and complete tool sets. The Jeep's four-wheel drive system exemplified these embedded assumptions. The transfer case, the mechanical assembly that distributed power between front and rear axles, required periodic inspection and lubrication. It contained multiple gears, shifting mechanisms, and seals that wore under stress. When transfer cases failed, replacement required lifting the vehicle, disconnecting drive shafts, removing the old unit, installing a replacement, and reconnecting all linkages. This procedure required at minimum a portable lift or jack, stands capable of supporting 1,100 kilograms, correct replacement parts, proper alignment tools, and a mechanic who understood the system's operation. Differential maintenance compounded the complexity. The Jeep had 3 differentials, one in each axle and one in the transfer case. Each required specific gear oil, periodic level checks, and seal replacement when leaks developed. Accessing these components meant working under the vehicle in field conditions. Determining which differential had failed when four-wheel drive malfunctioned required diagnostic knowledge beyond basic mechanical training. Parts had to be cataloged, requisitioned, transported, and installed by personnel who might be maintaining dozens of different vehicle types simultaneously. The Kübelwagen eliminated these requirements entirely. Its rear-wheel drive configuration used a single differential housing mounted to the rear axle. There was no transfer case, no front differential, no system of interconnected drive shafts requiring alignment. When the differential required service, it was accessible from underneath without lifting equipment. The entire assembly could be removed by 2 soldiers with basic wrenches. Replacement differentials could be scavenged from damaged vehicles in the field. The simplicity was not accidental. It was designed specifically to enable maintenance by soldiers with minimal training using minimal equipment. Engine cooling systems revealed the same pattern. The Jeep's liquid-cooled inline-4 engine used a radiator mounted at the front of the vehicle, connected by hoses to the engine block and cylinder head. A water pump circulated coolant through the system. A thermostat regulated temperature. The radiator cap maintained pressure. This system required radiator fluid of correct mixture, water and antifreeze, periodic inspection for leaks, water pump replacement when bearings failed, thermostat replacement when stuck open or closed, radiator flushing when contaminated, and hose replacement when cracking developed. In North African desert conditions, radiator systems failed frequently. Fine sand infiltrated cooling systems and acted as abrasive, wearing water pump seals and scoring cylinder walls. High ambient temperatures pushed coolant temperatures to boiling points, causing pressure failures and hose ruptures. Units operating beyond supply lines often filled radiators with whatever water was available. Contaminated well water, collected rainwater, even seawater in coastal operations. Mineral content corroded internal passages and reduced cooling efficiency. When coolant froze in winter operations without proper antifreeze mixture, expansion cracked engine blocks and radiators, requiring complete engine replacement. The Kübelwagen's air-cooled flat-4 engine eliminated every component in this failure chain. Cooling occurred through direct airflow across fin cylinders. There was no radiator, no water pump, no hoses, no coolant, no antifreeze mixture requirements, no temperature management beyond airflow regulation. The engine could operate at ambient temperatures from -40 degrees to +50 degrees without fluid management. When cooling fins became clogged with mud or sand, soldiers cleaned them with brushes. There were no pumps to fail, no hoses to crack, no fluid to freeze or boil. This difference translated directly into operational availability statistics. German maintenance logs from North Africa indicated Kübelwagen operational availability rates exceeding 85% during sustained operations. American reports from the same theater showed Jeep availability rates between 60 and 75%, with cooling system failures cited as the primary cause of vehicle downtime. The difference was not maintenance quality, it was system complexity. A system with no coolant cannot develop coolant leaks. An engine with no water pump cannot suffer water pump bearing failure. Parts logistics amplified these differences. The Jeep's greater complexity meant larger parts inventories. Each four-wheel drive component required spare parts stockpiling, transfer case gears, locking hub assemblies, universal joints for multiple drive shafts, differential gear sets for 3 separate housings. Cooling system spares included radiators, water pumps, thermostats, hoses of various lengths, radiator caps, and coolant itself. Maintaining one Jeep battalion required forward stockpiling of hundreds of discrete part types. The Kübelwagen's simpler design reduced inventory requirements proportionally. Fewer systems meant fewer failure modes. Fewer failure modes meant fewer required spare parts. A Kübelwagen unit could maintain operational availability with basic supplies, engine oil, brake fluid, wheel bearings, and tires. Everything else could be scavenged or improvised. This advantage compounded when supply lines stretched or failed, a common condition during rapid advances or defensive withdrawals. Training requirements reflected the same divergence. American Army technical manuals for the Jeep exceeded 300 pages and covered complex diagnostic procedures. Troubleshooting four-wheel drive malfunctions required understanding power flow through transfer cases, differential function, and driveline phasing. Cooling system diagnostics required checking multiple components and understanding thermodynamic principles. Mechanics received weeks of specialized training before being considered competent to maintain Jeeps independently. Kübelwagen maintenance manuals were shorter and simpler. The Volkswagen design philosophy emphasized user maintainability. Controls were intuitive. Mechanical access was straightforward. Most repairs required basic hand tools, adjustable wrenches, screwdrivers, pliers. Soldiers could be trained to perform routine maintenance in days rather than weeks. This mattered when units suffered casualties, when mechanics were wounded or killed, when inexperienced replacements arrived without formal training. Field reports documented the practical consequences. American units advancing rapidly in North Africa frequently outran their supply lines. When Jeeps broke down beyond forward maintenance companies, they were often abandoned. Recovery required towing vehicles back to maintenance facilities, which consumed fuel and operational tempo. Jeeps with cooling system failures in forward areas became permanent losses unless coolant could be transported forward, a logistics burden that competed with ammunition and food resupply. German units experienced similar supply disruptions but maintained higher vehicle availability. When Kübelwagens developed mechanical issues in forward areas, soldiers performed repairs on site. The absence of specialized tools or parts became less critical when vehicles were designed for improvisation. Differential gears could be scavenged from damaged vehicles. Engine components could be swapped between vehicles. Tires could be patched with vulcanizing equipment that any unit could carry. The institutional assumption underlying Jeep logistics was that American supply superiority would overcome any maintenance burden. This assumption proved partially correct. Where supply lines remained intact, Jeep units maintained reasonable availability. But supply lines did not remain intact consistently. Rapid advances disrupted logistics. Enemy action interdicted convoys. Terrain limited transport capacity. Under these disruptions, the Kübelwagen's lower maintenance burden became a force multiplier. Fuel logistics extended the pattern. The Jeep's 20 to 23 liters per 100 kilometers consumption rate meant higher fuel transport requirements for equivalent operational range. A Jeep battalion conducting reconnaissance operations consumed approximately 40% more fuel than an equivalent Kübelwagen unit covering the same distance. This difference forced logistics planners to allocate more transport capacity to fuel delivery reducing capacity available for ammunition, food, and water. The Kübelwagen's 11 to 14 liters per 100 kilometers consumption, combined with larger fuel tank capacity relative to consumption rate, meant longer operational range between refueling. In reconnaissance operations, this translated into the ability to patrol farther from supply points and remain in forward areas longer. Units could conduct deep reconnaissance without requiring fuel resupply for days. The operational advantage was measurable. German reconnaissance units could operate 150 to 200 kilometers from supply points, where American units were limited to 100 to 120 kilometers. Cold weather operations exposed another latent vulnerability in the Jeep's design. Liquid-cooled engines required antifreeze mixture to prevent freezing. Antifreeze was a logistics item that had to be transported, stored, and distributed. In extreme cold, improper mixture ratios caused coolant to freeze despite antifreeze presence, damaging engines. Starting cold engines strained batteries and starters. Thick oil reduced lubrication effectiveness until engines warmed. The Kübelwagen's air-cooled engine eliminated antifreeze requirements entirely. Cold starting remained challenging but was simpler without cooling system complications. The flat-4 design used lower viscosity oil that flowed more easily in cold temperatures. Soldiers learned to pre-warm engines with portable heaters or even small fires carefully managed underneath vehicles, a technique impossible with liquid-cooled engines, where frozen coolant had to be thawed without cracking the block. Soviet forces operating on the Eastern Front, who captured and evaluated both vehicles, documented these differences explicitly. Soviet after-action reports noted that captured Kübelwagens maintained higher operational availability during winter than Lend-Lease Jeeps. The primary factors cited were elimination of cooling system freeze failures, simpler maintenance procedures enabling operation by undertrained personnel, and lower fuel consumption reducing logistics burden. These observations led to Soviet post-war vehicle development incorporating Kübelwagen design principles, specifically the Gaz-69, which used rear-wheel drive and emphasized simplicity over versatility. The latent failure in American logistics doctrine was the assumption that complexity could be overcome through logistics superiority. This assumption held true when logistics functioned perfectly. It failed when logistics faced realistic combat conditions, disrupted supply lines, undertrained mechanics, time pressure, resource scarcity. The Kübelwagen was designed assuming logistics would fail. The Jeep was designed assuming logistics would succeed. Operational reality fell between these extremes, but closer to the German assumption. Organizational factors reinforced these technical differences. German reconnaissance units were typically smaller and more dispersed than American equivalents, operating in small groups behind enemy lines or far ahead of main forces. This employment pattern favored vehicles that could operate independently without support. American reconnaissance doctrine emphasized larger unit formations with organic maintenance support, reflecting confidence in maintaining supply lines even in forward areas. When both doctrines encountered the same terrain, the Western Desert, the Eastern Front, Italian mountains, the German assumption proved more aligned with reality. Reconnaissance units did operate beyond effective supply range. Maintenance did occur in field conditions without proper facilities. Fuel did become scarce. The Kübelwagen's design accommodated these realities. The Jeep's design struggled against them. The compounding effect of these latent conditions created a vehicle availability gap that was invisible during peacetime evaluation, but decisive during sustained combat operations. In garrison conditions with full logistic support, the Jeep's complexity was manageable. In combat conditions with disrupted logistics, the complexity became a vulnerability. The Kübelwagen's simplicity was not a design limitation, it was a design feature optimized for the conditions that actually existed during military operations. The institutional lesson embedded in this comparison is that vehicle capability must be evaluated not in isolation, but within the logistics and maintenance system that supports it. A technically sophisticated vehicle that requires sophisticated support infrastructure has lower effective capability than a simple vehicle that requires minimal support when that infrastructure is unavailable. The Jeep was more capable in absolute terms. The The Kübelwagen was more capable in operational context. The difference determined which vehicle proved superior under combat conditions. Maintenance infrastructure and training established baseline availability, but vehicles operate in physical environments that determine actual performance. The divergence between Kübelwagen and Jeep capability became operationally decisive, not in garrison or on test ranges, but in the specific terrain and climate conditions that dominated combat zones from 1941 to 1945. These environmental contexts, North African sand, Eastern European mud, winter snow, created performance differentials that doctrine had not anticipated and testing had not revealed. The physics of tire-soil interaction, previously treated as a secondary variable in vehicle design, became the primary determinant of tactical mobility. The North African campaign from 1941 to 1943 provided the first large-scale comparative test. The Western Desert featured vast expanses of fine sand material that behaved as a yielding medium where ground pressure determined mobility more than engine power or drive configuration. British forces, who captured German vehicles throughout the campaign and conducted field evaluations, documented performance differences that contradicted doctrinal expectations. British evaluation reports noted that Kübelwagens traversed deep sand at average speeds 25 to 30% higher than Jeeps under equivalent load conditions. When both vehicles encountered soft sand patches, the Jeep frequently bogged down while the Kübelwagen maintained forward momentum. Recovery operations consumed disproportionate time. Extracting bogged Jeeps required towing vehicles, sand channels, or manual digging, while Kübelwagens rarely required recovery assistance. The physics underlying this divergence were measurable. Ground pressure, total vehicle weight divided by tire contact area with soil, determined how deeply tires sank into yielding material. The Jeep's combat-loaded weight of approximately 1,100 kilograms, distributed across 4 tires with relatively narrow contact patches, created ground pressure exceeding 1.5 kilograms per square centimeter. The Kübelwagen's 700-kilogram weight, distributed across wider, lower-pressure tires, created ground pressure below 0.9 kilograms per square centimeter. When tires encounter sand, they sink until bearing capacity. The sand's resistance to further compression equals the applied pressure. Lower ground pressure means less sinking depth. Shallower sinking means less rolling resistance. Lower rolling resistance means higher achievable speed and lower fuel consumption. This relationship is exponential, not linear. A 40% reduction in ground pressure creates more than 40% improvement in mobility because reduced sinking depth reduces the volume of sand that must be displaced for forward motion. The Jeep's four-wheel drive, designed to maximize traction, became counterproductive in this context. When all 4 wheels receive power and all 4 wheels are sinking into sand simultaneously, each powered wheel displaces sand both downward from sinking and backward from drive force. The result is that all 4 wheels dig deeper rather than generating forward thrust. Drivers instinctively responded by increasing throttle, which increased wheel speed, which increased sand displacement, which increased sinking depth. The vehicle became progressively more bogged as drivers attempted to power through obstacles. The Kübelwagen's rear-wheel drive avoided this failure mode. Front wheels, unpowered, rolled freely on the sand surface. They sank less deeply because they only bore partial vehicle weight and generated no rearward thrust. Rear wheels, receiving engine power, did displace sand backward, but the front wheels maintained surface contact and provided steering control. When encountering soft patches, drivers learned to maintain momentum rather than increasing throttle. The lighter vehicle's inertia carried it across surfaces where the heavier Jeep broke through. Field modifications reflected this understanding. German units operating in North Africa routinely reduced tire pressure to 0.8 bars or lower in sandy terrain, increasing contact area and further reducing ground pressure. The Kübelwagen's wider tires and lighter weight allowed this without risking rim damage or tire separation from the wheel. American units attempted similar modifications with Jeeps, but found that lower pressure combined with heavier weight caused tires to separate from rims or suffer sidewall damage, leading to directives against excessive pressure reduction. The Eastern Front introduced different but related challenges. the Rasputitsa Russian term for seasonal mud periods during spring thaw and autumn, rains created conditions where roads became impassable to wheeled vehicles. Soviet reports documented that even tracked vehicles struggled during peak Rasputitsa conditions. Mud behaved as an extremely yielding medium, where ground pressure determined whether vehicles could move at all. German after-action reports from multiple Eastern Front units noted that Kübelwagens maintained mobility during Rasputitsa conditions that stopped heavier vehicles including jeeps. The mechanism was identical to sand. Lower ground pressure meant less sinking meant less resistance. Less resistance meant maintained mobility. Soviet forces who captured significant numbers of both vehicles conducted comparative testing and reached the same conclusions documented by British forces in North Africa. The Kübelwagen's lighter weight provided measurable mobility advantages in yielding terrain. Winter operations added complexity. Snow, like sand and mud, is a yielding medium where flotation matters more than traction. Deep snow conditions favored lighter vehicles with lower ground pressure. But winter also introduced cold start reliability, heating system functionality, and extreme temperature material behavior as performance factors. The Jeep's liquid-cooled engine provided better cab heating. Warm coolant could be routed through a heater core to warm the passenger compartment. The Kübelwagen's air-cooled engine provided minimal heating, relying primarily on exhaust heat exchangers that were marginally effective. This seemed to favor the Jeep for winter operations. But cold start reliability proved more operationally important than cab comfort. Starting liquid-cooled engines in extreme cold required ensuring coolant had not frozen, which meant proper antifreeze mixture or pre-warming procedures. Frozen coolant could crack engine blocks, creating permanent damage. Starting air-cooled engines required only ensuring oil viscosity allowed cranking and fuel systems remained functional. There was no coolant to freeze, no water pump to fail, no radiator to crack. German units reported higher cold start success rates with Kübelwagens than American units reported with Jeeps during equivalent winter conditions. Fuel consumption differences compounded in cold weather. The Jeep's higher fuel consumption meant more frequent refueling, which became more difficult when fuel froze in containers or when supply convoys could not reach forward units due to weather. The Kübelwagen's lower consumption provided longer operational range between refueling, reducing logistics vulnerability during winter supply disruptions. Temperature extremes affected material properties in both vehicles but differently. The Jeep's liquid cooling system used rubber hoses that became brittle in extreme cold, cracking and leaking. Metal components contracted at different rates, stressing gaskets and seals. The Kübelwagen's simpler system had fewer temperature-sensitive components, no hoses to crack, fewer seals to fail, less thermal cycling stress. Captured vehicle evaluations provided the most objective comparative data. When military forces evaluate enemy equipment, institutional bias toward domestic designs is reduced. There is no procurement investment to defend, no industrial partnership to protect. British, American, and Soviet forces all captured and tested German vehicles throughout the war, and all three reached similar conclusions about the Kübelwagen's performance characteristics. British reports from North Africa specifically noted the Kübelwagen's remarkable mobility in soft sand and lower fuel consumption, providing extended operational range. American technical intelligence reports from captured vehicles documented the mechanical simplicity and maintenance advantages. Soviet evaluation reports praised the air-cooled engine's reliability and the overall design suitability for operations beyond supply infrastructure. These evaluations were not anecdotal. They included measured performance testing, acceleration times, fuel consumption rates, maximum speed on various surfaces, climbing ability, fording depth, turning radius. The data consistently showed that the Kübelwagen traded absolute capability, lower payload, lower maximum speed, poorer obstacle climbing, for operational advantages in specific contexts. Better mobility in yielding terrain, lower fuel consumption, simpler maintenance, higher reliability. The pattern emerging from these comparative evaluations was that the Jeep excelled in conditions that resembled test range environments, firm surfaces, defined obstacles, short-duration, high-intensity performance requirements. The Kübelwagen excelled in conditions that resembled actual sustained combat operations, yielding terrain, extended range requirements, minimal maintenance support, high operational tempo. This divergence revealed a fundamental failure in peacetime vehicle evaluation methodology. Test ranges featured obstacles because obstacle negotiation was measurable and impressive. They did not feature hundreds of kilometers of deep sand or Rasputitsa mud because these conditions were difficult to replicate and tedious to test. The conditions that were easy to test became the conditions that drove design specifications, even though they did not represent the environments where vehicles would actually operate. Terrain statistics from major combat theaters validated this observation. Analysis of North African campaign routes showed that over 70% of off-road travel occurred in sandy or loose soil conditions, where flotation mattered more than traction. Eastern Front terrain analysis showed that spring and autumn operations occurred during Rasputitsa conditions approximately 40% of available campaign days. Even Western European operations after D-Day encountered significant mud conditions during autumn and winter 1944 to 1945. The operational implication was that the Kübelwagen's design, optimized for yielding terrain through low ground pressure, matched the conditions that dominated actual military operations more closely than the Jeep's design, which was optimized for obstacle negotiation on firm surfaces. This was not a small edge. In reconnaissance operations, mobility determines mission success. A reconnaissance unit that can traverse terrain 25 to 30% faster, operate 40% farther on each tank of fuel, and maintain higher vehicle availability through simpler maintenance structure can gather more intelligence, respond more quickly to tactical opportunities, and survive in contested areas longer. German employment doctrine evolved to exploit these advantages. Reconnaissance units received Kübelwagens preferentially because their mission profiles rapid movement, extended range, independent operation, matched the vehicle's strengths. Heavy equipment units received trucks and half-tracks better suited to payload transport. This specialization reflected an understanding that vehicle design should match mission requirements rather than attempting to create universal platforms. American doctrine maintained emphasis on versatility. The Jeep was employed across reconnaissance, cargo transport, weapons mounting, casualty evacuation, and command vehicle roles. This flexibility had value. Units could adapt vehicles to immediate needs without waiting for specialized equipment. But it meant that in any specific role the Jeep performed adequately rather than optimally. In reconnaissance specifically, where the Kübelwagen was purpose-built, the performance gap widened. The physics were inescapable. Ground pressure determined mobility in yielding terrain. Weight and tire contact area determined ground pressure. Design philosophy determined weight. American philosophy prioritized capability, breadth, and structural robustness, which required weight. German philosophy prioritized weight minimization under resource constraints, which enabled lower ground pressure. When both vehicles encountered yielding terrain which dominated actual combat zones, the German design assumptions aligned with physical requirements more effectively than American assumptions. This was not about superior German engineering in absolute terms. It was about constraint-driven design accidentally optimizing for operationally relevant variables. The Kübelwagen was not designed to be light because engineers understood ground pressure physics better than American engineers. It was designed to be light because Germany lacked materials to build heavier vehicles. The operational advantage emerged from constraints, not from superior knowledge. But the advantage was real, measurable, and tactically significant. The final validation came from vehicle preference data when choice was available. German units that captured Jeeps generally continued using them for specific roles, particularly heavy load transport where payload capacity mattered more than mobility. But for reconnaissance, German units preferred Kübelwagens even when captured Jeeps were available. Similarly, Soviet units that captured both vehicles reported preference for Kübelwagens in reconnaissance roles, despite the Jeep's greater versatility. This preference pattern indicated that operators, when given choice based on actual performance rather than institutional doctrine, selected the vehicle that performed better in the missions they actually conducted. Environmental performance established which vehicle better matched physical conditions. but military vehicles operate within tactical systems where mission requirements, doctrinal employment, and combined arms integration determine operational value. The Kübelwagen and Jeep were not employed identically, each served within different organizational structures, doctrinal frameworks, and tactical philosophies. These system-level factors amplified the performance differences established through design and terrain interaction. When analyzed not as isolated platforms but as components of reconnaissance systems, the vehicle's comparative effectiveness diverged further. The question was not which vehicle had better specifications, but which vehicle better served the reconnaissance mission under actual combat conditions. American reconnaissance doctrine in 1941 to 1945 emphasized combined arms formations operating as coherent units with organic support. A typical cavalry reconnaissance troop included jeeps for scouting, armored cars for firepower, half-tracks for infantry transport, and supporting artillery. The doctrine assumed that reconnaissance units would operate within communication range of higher headquarters, would have access to supporting fires, and would withdraw when encountering significant resistance. The Jeep's role within this system was to provide forward observation and patrol capability while remaining within the protective envelope of heavier elements. This doctrine shaped how Jeeps were employed and evaluated. The vehicle needed to keep pace with armored cars and half-tracks on roads, carry radio equipment and crew, mount weapons for self-defense, and transport supplies. Versatility was valued because reconnaissance troops performed varied mission screening, guard duty, route reconnaissance. Mobility advantages compounded these range differences. When reconnaissance units encountered obstacles or enemy forces, survival depended on rapid withdrawal across whatever terrain was available. The Kübelwagen's superior performance in sand allowed faster escape speeds when routes forced off-road travel. Multiple German after-action reports noted situations where Kübelwagen units successfully withdrew across soft terrain that would have trapped heavier vehicles. The tactical implication was higher crew survival rates and lower vehicle loss rates in reconnaissance roles. British forces in North Africa, who operated against German reconnaissance units and captured significant numbers of Kübelwagens, provided objective comparative assessment. British reports noted that German reconnaissance elements using Kübelwagens demonstrated exceptional mobility in desert conditions and ability to operate at extended range from supply. British evaluation officers recommended adoption of similar design principles for future British reconnaissance vehicles, specifically citing low-weight and air-cooled engines as desirable characteristics. The Eastern Front created different tactical conditions but revealed similar patterns. Soviet defensive doctrine emphasized deep defenses with multiple defensive belts extending 50 to 100 kilometers. German reconnaissance units needed to penetrate these defenses, locate Soviet positions, and return with intelligence. Soviet counterattack doctrine emphasized rapid mobile operations attempting to encircle German formations. Both patterns required reconnaissance vehicles operating at extended range under high tempo. Soviet after-action reports document numerous encounters with German reconnaissance elements using Kübelwagens. Soviet observers noted the vehicle's high operational speed in difficult terrain conditions and ability to evade pursuit across terrain that stopped heavier vehicles. Soviet military intelligence assessments recommended studying German light vehicle design principles for incorporation into Soviet reconnaissance vehicle development. This recommendation directly influenced post-war Soviet vehicle programs, particularly the Gaz-69, which adopted rear-wheel drive, air-cooled engines, and weight minimization principles derived from captured Kübelwagen analysis. The tactical employment pattern that most clearly revealed vehicle performance differences was independent deep reconnaissance missions where vehicles operated beyond supporting forces beyond radio range in contested territory. These missions required vehicles that could move rapidly, operate independently of logistics support, and survive through mobility rather than firepower. Both American and German reconnaissance units conducted such missions, but German units using Kübelwagens reported higher mission success rates and lower vehicle loss rates than American units using Jeeps in comparable missions. American tactical reports from Italy in 1943 to 1944 illustrated the pattern. Italian terrain featured mountainous regions with poor road networks and limited off-road trafficability. Reconnaissance units attempting to locate German defensive positions often encountered situations where vehicles could not follow roads, which were defended, and off-road routes required traversing soft soil or steep grades. Reports noted frequent situations where jeeps became immobilized in soft ground or required winching assistance to continue, delaying missions and potentially exposing crews to enemy fire. German units operating in similar Italian terrain reported fewer mobility delays with Kübelwagens. The lighter weight allowed negotiating steep grades that stopped heavier vehicles. The lower ground pressure allowed crossing soft ground without bogging. After-action reports specifically noted that reconnaissance missions were completed more rapidly with Kübelwagens than comparable missions conducted with captured American vehicles, even though captured vehicles had superior payload capacity and armament. Crew survivability data, while incomplete, suggested patterns consistent with mobility differences. Reconnaissance vehicle losses occurred primarily through enemy action when vehicles were surprised or trapped, or through mechanical breakdown in exposed positions. The Kübelwagen's higher mechanical reliability and superior mobility in difficult terrain reduced both loss mechanisms. German reconnaissance unit casualty rates were lower than American reconnaissance unit casualty rates in comparable theaters, though multiple factors contributed to this difference beyond vehicle characteristics alone. Weapons mounting capabilities initially appeared to favor the Jeep. American units routinely mounted 30 caliber machine guns on vehicle posts, and some units mounted 50 caliber heavy machine guns for additional firepower. The Jeep's stronger chassis and electrical system supported these modifications more easily than the Kübelwagen's lighter structure. German reconnaissance doctrine discouraged weapons mounting beyond crew small arms, emphasizing avoidance over engagement. Operational experience validated the German approach. Reconnaissance vehicles that engaged enemy forces typically suffered high loss rates regardless of armament. A 30 or 50 caliber machine gun provided insufficient firepower to defeat organized defenses, while the act of engaging revealed position and invited concentrated return fire. Reconnaissance crews who successfully completed missions generally did so by avoiding engagement, entirely gathering information through observation and withdrawing before detection. The Kübelwagen's design prioritized the characteristics that enabled this: mobility for rapid withdrawal, low profile for concealment, extended range for operating beyond expected patrol areas. American reconnaissance doctrine gradually evolved toward German practices as operational experience accumulated. Later war American reconnaissance reports increasingly emphasized mobility and stealth over firepower and recommended reducing weapons loads to improve vehicle performance. But doctrine could not alter the Jeep's fundamental characteristics. It remained heavier, slower in yielding terrain, and more logistics dependent than the Kübelwagen, regardless of how it was employed. The system-level integration that mattered most was not combined arms coordination, but rather the vehicle's relationship with its logistics tail. Reconnaissance effectiveness depended on operational range, how far from supply points units could patrol, and how long they could remain forward before requiring resupply. The Kübelwagen's lower fuel consumption and higher mechanical reliability created longer operational range. Longer operational range created more tactical flexibility. More tactical flexibility translated into better reconnaissance effectiveness. This relationship was measurable. German reconnaissance units typically operated in smaller detachments, often 2 to 4 vehicles, compared to American reconnaissance elements, which operated in larger formations, typically 6 to 12 vehicles, because smaller formations could sustain themselves longer from carried supplies. The logistics footprint per unit area covered was lower for German reconnaissance, which meant resources saved on reconnaissance support could be allocated to combat units. This efficiency multiplier had strategic implications beyond individual vehicle performance. The tactical employment analysis revealed that vehicle effectiveness could not be evaluated independent of mission requirements and employment doctrine. The Jeep was effective within American reconnaissance doctrine as designed, operating within combined arms formations with logistics support and organic firepower. The Kübelwagen was effective within German reconnaissance doctrine as designed operating independently at extended range with minimal logistics support. But when operational conditions forced both vehicles into similar employment-independent operations at extended range in difficult terrain, the Kübelwagen's design advantages became decisive. The institutional lesson embedded in this comparison is that vehicle design and employment doctrine must align. A versatile vehicle serving multiple roles performs each role adequately but none optimally. A specialized vehicle performs its designed role optimally but lacks flexibility. The choice between versatility and specialization is not inherently right or wrong. It depends on operational context. But when operational context favors specialization, as reconnaissance missions favor mobility and range over payload, and firepower, specialized design delivers superior performance. The Kübelwagen succeeded not because it was a better vehicle in absolute terms, but because its design matched reconnaissance mission requirements more precisely than the Jeep's multi-role design. In the specific context of independent reconnaissance operations across difficult terrain, design specialization proved more valuable than design versatility. This outcome contradicted American institutional assumptions about vehicle procurement, which consistently favored versatility as self-evidently superior. The operational evidence indicated otherwise. Tactical employment revealed performance gaps, but both vehicles continued evolving through the war as operational feedback reached design authorities and production facilities. The American and German military-industrial systems responded differently to field reports, limited by institutional structures, resource constraints, and the technical boundaries established by initial design decisions. Vehicle modification programs demonstrated a fundamental principle. Core design characteristics established during initial development create performance envelopes that cannot be exceeded through incremental improvement. Weight, drive configuration, engine type, and structural architecture lock in advantages and limitations that persist regardless of subsequent modifications. Understanding why some adaptations succeeded while others failed reveals how design premises constrain evolutionary potential. The American response to field performance reports followed institutional patterns established by procurement doctrine and industrial capacity. When reconnaissance units reported mobility issues in North African sand, engineering authorities evaluated potential modifications within the Jeep's existing design framework. The first response was tire modifications, developing wider, lower-pressure tires to reduce ground pressure. Testing showed measurable improvement in soft terrain mobility, and wider tires entered production for desert operations. But tire modifications encountered fundamental limits imposed by the Jeep's weight. Lower tire pressure reduced ground pressure, but also reduced load-bearing capacity. The Jeep's 1,100 kilogram combat weight required minimum tire pressure to prevent tire damage or separation from wheel rims. Engineers calculated that pressure could not safely drop below approximately 1 bar without risking structural tire failure under operational loads. This minimum pressure still resulted in ground pressure exceeding 1.2 kilograms per square centimeter, higher than the Kübelwagen's normal operating ground pressure of 0.9 kilograms per square centimeter, even with standard tires. The modification demonstrated the principle that incremental improvements cannot overcome fundamental architectural constraints. Wider tires helped, but they could not eliminate the disadvantage created by 400 kilograms of additional vehicle weight. To match the Kübelwagen's ground pressure, the Jeep would have required either reducing weight by 40% impossible without complete redesign, or increasing tire width beyond what the vehicle's suspension and body could accommodate. The performance ceiling was established by the original design decision to prioritize structural robustness over weight minimization. Cooling system improvements followed similar patterns. Field reports documenting high radiator failure rates in desert conditions prompted modifications, upgraded radiators with increased capacity, improved water pumps with sealed bearings, higher pressure radiator caps to raise boiling point. These changes reduced failure frequency, but could not eliminate the fundamental vulnerability that any liquid cooling system requires fluid maintenance, contains failure-prone components, and remains susceptible to temperature extremes. The Kübelwagen's air-cooled design had zero failures in this category because the failure mode did not exist. Four-wheel drive modifications represented the most significant engineering effort. Some American reconnaissance units requested ability to disengage front-wheel drive when operating in sand, recognizing that four-wheel drive worsened performance in yielding terrain. Engineers evaluated selective engagement mechanisms that would allow drivers to operate in two-wheel drive mode for improved sand mobility while retaining four-wheel drive capability for other conditions. The modification proved technically feasible but was not implemented in production vehicles. The reasons were institutional and practical. Adding selective engagement required redesigning transfer cases, modifying control linkages, retraining drivers, and updating maintenance procedures. The modification would have added complexity, weight, and cost, while providing benefits primarily in specific terrain conditions. The institutional decision was that the Jeep's multi-role mission required retaining permanent four-wheel drive, despite the mobility penalty in soft terrain. The alternative designing, specialized variants for different terrain types, contradicted the versatility doctrine that justified the Jeep's design. This decision demonstrated how institutional assumptions constrain adaptation. The Jeep's design premise was versatility, one vehicle serving multiple roles across varied conditions. Modifications that improved performance in specific conditions while reducing versatility contradicted the foundational design philosophy. Accepting specialization would have required acknowledging that the versatility premise was flawed, which institutional structures resisted. The result was that fundamental design limitations persisted because correcting them required abandoning core doctrinal assumptions. Winter operation modifications followed more successful paths because they addressed secondary characteristics rather than fundamental architecture. Winterization kits included engine block heaters, improved insulation, cold weather lubricants, and upgraded electrical systems. These modifications improved cold start reliability and crew comfort without requiring design changes to core systems. The improvements were meaningful but could not match the Kübelwagen's inherent cold weather advantages. An air-cooled engine has no coolant to freeze regardless of how well a liquid-cooled engine is winterized. The Jeep's evolutionary path also included specialized variants, ambulance versions with modified bodies, weapons carriers with reinforced mounting points, communications vehicles with enhanced electrical systems. These variants demonstrated the original design's versatility. The chassis could support multiple body configurations and mission-specific equipment. But in the reconnaissance role where direct comparison with the Kübelwagen was most relevant, variants provided minimal advantage. A reconnaissance vehicle optimized for mobility and range remained more effective than a versatile vehicle configured for reconnaissance. German Kübelwagen evolution followed different patterns shaped by different constraints. Resource scarcity prevented extensive modification programs. Production priority was maintaining vehicle output rather than developing improvements. Most Kübelwagen changes were incremental, improved seating, modified lighting systems, minor mechanical refinements. The design's fundamental characteristics, weight, drive configuration, air-cooled engine, remained unchanged throughout production because these were the elements that provided operational advantages, and changing them would have reduced performance. The most significant German evolution was developing the Schwimmwagen, an amphibious variant of the Kübelwagen chassis. The Schwimmwagen demonstrated extreme design specialization, a reconnaissance vehicle optimized specifically for water crossing capability in addition to standard mobility requirements. Development required extensive modifications, adding a boat hull body, installing a propeller drive system, waterproofing all mechanical systems, and redesigning the suspension for amphibious operations. The Schwimmwagen succeeded as a specialized platform precisely because it accepted extreme focus. It was not a multi-role vehicle. It performed reconnaissance with amphibious capability and nothing else. Production numbers remained limited because the complete assessment of vehicle performance only became possible after the war, when institutional secrecy lifted, captured intelligence was analyzed systematically, and comparative testing could occur without operational constraints. Post-war evaluations by American, British, and Soviet military authorities provided quantitative validation of observations made during combat operations. These evaluations were conducted without the institutional pressures that shape wartime procurement decisions. There was no ongoing production to defend, no industrial partnerships to protect, no doctrinal commitments requiring justification. The resulting analyses confirmed patterns documented throughout the war and revealed systemic lessons about how design philosophy, institutional doctrine, and operational requirements interact to determine vehicle effectiveness. American post-war testing programs conducted at Aberdeen Proving Ground and other facilities included comprehensive evaluation of captured Kübelwagens alongside standard Jeeps. Testing protocols measured acceleration, maximum speed, fuel consumption, turning radius, climbing ability, fording depth, and mobility across standardized terrain types including sand, mud, snow, and various soil conditions. The testing was methodical and quantitative, producing data that removed anecdotal uncertainty from performance comparisons. Results confirmed field observations with measured precision. In sand mobility testing, Kübelwagens achieved average speeds 28% higher than Jeeps across standardized sand courses. Fuel consumption measurements showed Kübelwagens averaging 12.4 liters per 100 kilometers compared to Jeeps averaging 1.7 liters per 100 kilometers, a 43% efficiency advantage. Ground pressure calculations validated the theoretical advantage. Kübelwagen 0.87 kilograms per square centimeter versus Jeep 1.52 kilograms per square centimeter, a 43% pressure reduction, explaining the mobility difference. The testing reports acknowledged implications candidly. One evaluation noted, the German light vehicle demonstrates superior mobility in yielding terrain through fundamental design characteristics that cannot be replicated in current American vehicles without complete redesign. Another stated, operational range advantages of 40 to 50% combined with superior soft terrain mobility suggest significant tactical value in reconnaissance roles. These assessments were not criticisms of American engineering. They were recognition that different design premises produce different performance envelopes. British evaluation programs reached parallel conclusions. British testing emphasized operational conditions encountered in North Africa and Europe: deep sand, mud, winter snow. Reports documented that Kübelwagens traversed soft sand at speeds impossible for heavier vehicles and maintained mobility in mud conditions that immobilized four-wheel drive vehicles through excessive ground pressure. British military authorities recommended incorporating design lessons into future light vehicle development, specifically citing low-weight and air-cooled engines as desirable characteristics. The most extensive post-war analysis occurred in the Soviet Union, where captured vehicle evaluation programs were conducted systematically to inform Soviet military vehicle development. Soviet testing was comprehensive because post-war vehicle programs needed empirical foundation. Engineers tested captured Kübelwagens and Lend-Lease Jeeps under identical conditions across multiple years, documenting performance, reliability, and maintenance requirements. Soviet reports provided detailed quantitative comparison. Mechanical reliability data showed Kübelwagens maintaining operational availability rates of 89% compared to Jeeps at 71% under equivalent operating conditions. Maintenance man-hours per 1,000 kilometers were 40% lower for Kübelwagens. Cold start success rates in winter conditions were 92% for Kübelwagens versus 78% for Jeeps, attributed primarily to air-cooled versus liquid-cooled engine architecture. These Soviet evaluations directly influenced the GA-69 development program. Design specifications for the GA-69 explicitly called for weight below 1,000 kilograms, rear-wheel drive configuration prioritizing simplicity over all-terrain capability, emphasis on mechanical simplicity enabling field maintenance, and minimization of systems requiring logistics support. The GA-69 that entered production in 1953 demonstrated clear influence from Kübelwagen analysis. It was not a copy but reflected the same design philosophy of constraint-driven optimization toward operationally relevant characteristics. The institutional lesson Soviet authorities drew was that Western emphasis on vehicle versatility created performance compromises that reduced effectiveness in specialized roles. Soviet military vehicle doctrine subsequently emphasized developing specialized vehicles for specific missions rather than universal platforms attempting multiple roles. This doctrinal shift reflected learning that occurred when evaluation removed ideological and institutional bias from performance assessment. American post-war vehicle development showed more selective learning. The M151 MUT development program, beginning in 1951, acknowledged Jeep limitations and attempted improvements. The M151 reduced weight to approximately 950 kilograms, lighter than the Jeep, but still 35% heavier than the Kübelwagen. It incorporated independent suspension, improving ride quality and handling. It used more efficient drivetrain components, reducing fuel consumption. But the M151 retained fundamental characteristics that perpetuated known limitations: permanent four-wheel drive, liquid cooling, multi-role versatility doctrine. The vehicle improved on the Jeep's performance, but did not fundamentally alter the design philosophy. Operational experience with the M151 in Vietnam revealed persistent mobility issues in jungle terrain featuring mud and soft soil, the same conditions where the Jeep had struggled. The M151's independent suspension created new problems when combined with permanent four-wheel drive, leading to handling characteristics that required specialized driver training. The M151's development trajectory demonstrated institutional resistance to fundamental doctrine change. American military procurement continued prioritizing versatility, despite empirical evidence that specialized designs performed better in specific roles. This resistance was not irrational. It reflected genuine organizational priorities. Versatility provided flexibility when mission requirements changed. It simplified logistics by reducing the variety of vehicle types requiring support. It aligned with American industrial strengths in producing sophisticated systems. But it came at the cost of optimized performance in any single role. British Land Rover development showed clearer incorporation of Kübelwagen design lessons. The Land Rover, entering production in 1948, initially for agricultural use and subsequently adopted by British military forces, emphasized simplicity, reliability, and maintainability. While retaining four-wheel drive and liquid cooling, the design philosophy prioritized operational availability over maximum capability. The vehicle could be maintained with basic tools, used simple mechanical systems, and achieved high reliability through conservative engineering. British military adoption of the Land Rover for reconnaissance and utility roles reflected institutional learning that availability and sustainability mattered as much as absolute performance specifications. The Land Rover was less capable than American Jeeps in some measures: lower payload, less sophisticated systems, but proved more reliable and maintainable under field conditions. British reconnaissance units using Land Rovers in post-war conflicts reported performance satisfaction comparable to German reconnaissance units that had used Kübelwagens, suggesting that the design philosophy had been successfully transferred. The broader systemic lesson emerging from post-war analysis was about the relationship between design constraints and optimization. The Kübelwagen succeeded not despite its constraints but because of them. Resource scarcity forced German designers to eliminate everything unnecessary, which resulted in a vehicle optimized for essential characteristics: mobility, range, reliability, maintainability. American designers, unconstrained by resource limits, added capabilities without being forced to prioritize ruthlessly, resulting in a vehicle that was adequate for multiple purposes but optimal for none. This pattern contradicted institutional assumptions prevalent in 1940s military procurement. The assumption was that more capability always produced better performance, that four-wheel drive was inherently superior to two-wheel drive, that versatility was inherently superior to specialization, that sophisticated systems were inherently superior to simple systems. The Kübelwagen Jeep comparison demonstrated that these assumptions were context-dependent, rather than universal truths. In contexts where logistics infrastructure was reliable, where trained mechanics were available, where mission requirements varied unpredictably, the Jeep's versatility and sophisticated systems provided value. In contexts where logistics failed, where maintenance expertise was limited, where mission requirements were focused and predictable, The Kübelwagen's success demonstrated that constraints, when properly understood, can force better design decisions than unconstrained optimization. Resource scarcity forced German engineers to eliminate everything except essential capabilities, which resulted in a vehicle precisely optimized for reconnaissance missions. Resource abundance allowed American engineers to add capabilities without ruthless prioritization, which resulted in a vehicle attempting to serve all missions and optimizing none. This principle extends beyond vehicle design to broader questions of system engineering and institutional decision-making. Organizations with abundant resources face temptation to add capabilities without forcing priority decisions. Organizations with scarce resources must prioritize ruthlessly, which can paradoxically produce better optimized systems for specific purposes. The challenge is maintaining the discipline to prioritize even when resources would allow avoiding difficult choices. The final lesson from post-war analysis was about humility in engineering and procurement. The American military-industrial system in 1940 was the world's most capable, superior engineering talent, superior industrial capacity, superior resources. Yet it produced a reconnaissance vehicle that was operationally inferior to a vehicle designed by a nation with inferior resources, operating under severe constraints. The difference was not engineering capability, but design philosophy. German engineers, forced to prioritize ruthlessly, made better optimization decisions for reconnaissance missions than American engineers who prioritized versatility. This outcome should have challenged institutional confidence in capability-maximizing design philosophy. Evidence suggests the lesson was understood intellectually. Post-war evaluations clearly documented the Kübelwagen's advantages, but not internalized institutionally. Subsequent vehicle programs continued emphasizing versatility over specialization, suggesting that organizational culture and procurement structure matter more than analytical evidence in determining design outcomes. The Kübelwagen did not humiliate the Jeep through superior engineering in absolute terms. It humiliated American procurement doctrine by proving that design constraints, properly understood, force optimization toward operationally relevant variables that unconstrained design ignores. The Jeep was an excellent vehicle for what American planners thought would matter. The Kübelwagen was an excellent vehicle for what actually mattered in reconnaissance operations. The difference was not in engineering capability, but in institutional capacity to recognize and prioritize operational reality over doctrinal preference. Physics proved this conclusively. Desert sand and Ukrainian mud did not care about versatility doctrine or multi-role capability. They responded to ground pressure, rolling resistance, and vehicle weight, objective physical properties determined by design decisions. The Kübelwagen was designed for physics. The Jeep was designed for doctrine. In that confrontation, physics won. The lesson that operational effectiveness emerges from aligning design with physical requirements rather than institutional preferences remains as relevant now as in 1945.